Alright, so in this section we're going to be discussing a new test for determining if an integral converges or diverges. And then we're going to use basically this test to develop what's called a remainder estimate. So we won't get what the sum is exactly equal to, but we can get some kind of bounds on where the sum must lie. Right, so we could have this super complicated sum, and we'll know that when you add everything up, it gets somewhere between 1 and 2. Or if I want to calculate S5, right, the sum of the first 5 partial terms, then we'll be able to determine how far off that is from the actual sum. Or at least the range in which it lies from the actual sum. Alright, so what's important to notice here is that we use the integral test whenever our sequence is made up of only positive terms. So what we're going to have is we'll have some sequence. So let's say we have something like a sub n equals n. Right? This is the sequence 1, 2, 3, 4, 5, 6. And then I want a function that kind of models that sequence. So for this, I would do f of x equals x. Because if I plug in n for x, then I'm going to get, so if I plug in 2, then I would get f of 2 equals 2. And that's what the second term of the sequence should be. Let's say I had something like, say, n squared plus 1. Then we would know that a sub 3 is going to be equal to 9 plus 1, which is 10. So I want some function, f of x, such that, say I want to calculate a sub 3. If I want to calculate a sub 3, then I'm plugging in 3 into this function. And I want it to be the same thing as a sub 3, so I'm going to make this n squared plus 1. Similarly, someone could just give us a sequence of numbers, right? So we could do something like 7, 2 over 7, 4 over 49, and so on, right? We know this sequence. This is a geometric sequence. So once we determine what a sub n is, we know that a sub n is going to be 7 times 2 sevenths to the n minus 1. Then I know that my f of x function, right, this f of k, is going to be 7 times 2 sevenths to the x minus 1. Okay? Now, so we've talked about kind of what we're doing here. What we need is that when we model our sequence with this f of x function, we need f of x to be continuous, positive, and decreasing on the interval that we're summing over. Right, so the interval that comes from, if I give you something like the sum from n equals 3 to infinity, then the interval that I'm looking at is 3 to infinity. So whatever my function is, I want to make sure that it's continuous on this interval, all of my values are positive, and that it's strictly decreasing. If we have something like that, then we get that this sum and this integral, they either both converge or both diverge. Okay? And this is what's known as the integral test. And quick note, I believe that this section, this video, is going to be a little bit more fruitful than my last video because I didn't use the color plum, and now we'll make the return of the color plum. Alright, so if we're using the integral test and we get that, this integral is equal to a, this does not mean that the sum is equal to a. All the integral test says is that they either both converge or they both diverge. It does not mean that they're equal. Let's look at an example of why this is true. So first of all, this should be the integral from 1 to infinity. Alright, and so this sum, for this sum, what we're doing is we're taking these y values and adding them together. Right, we're adding together infinitely many of these. Now what the integral is doing, if we're integrating from 1 to infinity, then the integral is calculating all of this area under the curve. Right? If my f of x function is given by this green line, let's see. Right? That's our f of x function right there. Then what the integral is doing is it's calculating all of this area underneath the curve. Now, let's see what happens. When we're doing that, well, we would want the area that's kind of shaded in gray. We want that area. However, we're also going to be getting this extra area that is not represented by terms of our sequence, right? That isn't going to be in the series. And so what's going to happen is that this integral is going to be greater than or equal to our sum, right? And so that's one case where the integral and the sum are not going to be equal. Now, if we have some case like this over here on the right, then the integral is going to calculate all of this area under the curve. But notice that the sum goes above our function slightly. So what's going to happen is the sum is going to be calculating all of this extra amount, right? And so in this case, we can say that our sum is going to be greater than the integral, right? So this is just some support for reasoning for why these two are not equal, okay? Now, if you look in the book or maybe at other people's notes, you'll see that my integral test may look slightly different. The only difference should be is that in the book they'll use k equals 1 right here, and m would be 1 right there. Right? That's the only difference. What I've done here is I've generalized this to where we can start at some number m instead of starting at 1. So let's see. Let's try to start using this integral test. So this right here is going to be my sequence, and I want a function that models this sequence. So I'm going to use f of x equals x over x plus 1. Now, before I get started on doing the integral test, I want to mention something that I mentioned in the last video, which is that you should always use the test for divergence first. It's going to be much faster than any of our other tests. And if I use the test for divergence here, let's remember that the test for divergence says if we take the if the limit as n goes to infinity of a sub n, right? Notice we're taking this limit of the sequence, not of the partial sum sequence. So I'm using a sub n and not s sub n. If this limit is not equal to 0, then it diverges. And so this will be quick for us because we look at the limit as n goes to infinity of n over n plus 1. Using L'Hopital's rule, I can take a derivative of top and bottom to get that this is equal to 1. So we know, so that's not equal to 0, which means that it diverges by the test for divergence. There we go. Okay. Now we'll look at example 2. I noticed that using the test for divergence here, my denominator is going to go to infinity, so this limit will be equal to 0. Right? And remember that when the limit is equal to 0, the test for divergence doesn't tell us anything. So that's the first thing that I note, is that the test for divergence fails. Right? And so now we can start using our integral test. So I should have the integral from whatever the interval is for the sum, so our sum goes from 1 to infinity. So this is going to be the integral from 1 to infinity of the function that models our sequence. And so that function would be 1 over 7x plus 8 cubed. Now, I want to think about, is it appropriate for us to be using the integral test right now? Well, let's see. All of the x values that I'm plugging in are from 1 to infinity. So this denominator will never be equal to 0, which means that it's continuous. We're also not plugging in any negative numbers, so all of our numbers are going to be positive. We can also see that our denominator is going to be getting bigger like if we do x equals 1, x equals 1.5, x equals 2, and so on. All of those x values will be making our denominator bigger. So that means that this function is going to be decreasing. So we have the three things we need. We got continuity, we got positive, and we got decreasing. So now I know it's safe to use the integral test. So this is an improper integral. We'll rewrite it as the limit as t goes to infinity of the integral from 1 to t of 1 over 7x plus 8 cubed dx. Okay, and so now I can use a u sub. What I'm going to do is I'm going to u sub u equals 7x plus 8. And so that'll change this into 1/7 times the limit as t goes to infinity of the integral. We have to remember to change our limits, so we plug in 1. That'll give us 15, because 7 times 1 plus 8 is 15. Plugging it in up here. And then we'll also get 7t plus 8. And then in here, we should have 1 over u cubed du. Right, and so now I'll work on actually integrating this. So I've got 1/7 limit as t goes to infinity. And then for our integral, when we integrate u cubed, we should get -1 over 2 u squared. Evaluated from 15 to 7t plus 8. So this will be 1/7 times the limit as t goes to infinity of, let's see, so we should have -1 over 2, that's a interesting 2, 7t plus 8 squared. And then let's see, we should have minus -1 over 2 times 15 squared. And now what I notice here is that this part right here will go to 0 since the denominator runs off to infinity. So this is just going to be 1/7 times 1 over 2 times 15 squared. So this is, whatever it is, it's a finite number. And so we know that this integral converges, which means that the sum also converges. All right, and so this is how we use the integral test. And we often rewrite it as this improper integral. We calculate our improper integral, and then if that improper integral converges, then our sum also converges. If it diverges, then our sum also diverges. All right, now let's look at example 3. First thing I should do is the test for divergence. Well, for the test for divergence, we'd use L'Hopital's rule. We'd get 1 over 2n. The limit as n goes to infinity of that is going to be 0. So we know that our test for divergence fails. All right, so now we can rewrite this as the integral from 1 to infinity of x over x squared plus 1 dx. So we rewrite this as a limit. Limit as t goes to infinity. Integral from 1 to t of x over x squared plus 1 dx. And this is one of our more complicated u sub problems. Sorry, no it's not. This one will actually work out. So here we'll do u equals x squared plus 1. I was afraid at first that we'd have to back substitute, but we'll get a cancellation of x's. So this is going to become 1/2 limit as t goes to infinity. Integral from, so now I have to change my limits. This will become 1 squared plus 1, which is 2. And plugging in t, we get t squared plus 1. Make sure that if you aren't changing your limits here, you need to be writing, x equals 1 and x equals t on the limits. That's a really big way to get points taken off on a free response problem. Right, and then this should become 1 over u du. Alright, so now this will be 1/2 limit as t goes to infinity. Integrating 1 over u, we'll get the natural log of the absolute value u from 2 to t squared plus 1. So this is going to give me 1/2 limit as t goes to infinity of the natural log of the absolute value t squared plus 1 minus the natural log of the absolute value of 2, which is just the natural log of 2. And so here, this part will be going to infinity, so we're going to get 1/2 infinity minus ln 2, which will give us infinity. And so this tells me that the sum also diverges. Okay, now let's move on to example 4. Here, I notice, okay, if I want to use my test for divergence, then what I would get is we'd have some fraction n over e to the n squared. And so we could use L'Hopital's rule, or we can see that this exponential function is going to be growing faster than this linear function right here. And so the bottom's going to go to infinity much faster, which means that this limit's going to go to 0. So we know our test for divergence is going to fail. Now for using the integral test, we should have the integral, so now we're going from 0 to infinity, right? Because this goes from n equals 0 to infinity. Oh, and I forgot to verify something on example 3, which is that this function right here is continuous, positive, and decreasing. So it's continuous because our denominator will never be equal to 0. It's positive because we're only plugging in positive numbers on top and bottom. For decreasing, that's maybe a little bit harder, but the way we verify that is that this x squared plus 1 is going to grow much faster than x, so our values are going to be getting smaller and smaller. Right, to test this out, I could plug in, say, like 1. We would start out with 1/2. If I plug in 2, we'd get 2 over 5. And then so on, right? And so this 1/2, that's 0.5, 2/5 is 0.4, so this is getting smaller. All right. Now for example 4, we're going to have the integral from 0 to infinity of n e to the negative n squared. Right, and so like I was talking about before, this n e to the negative n squared, this is n over e to the n squared. So notice, even if I plug in 0 for n, we'd get 0 over 1, which is just 0. And so this is going to be continuous. We'll get positive terms on top and bottom, so this is going to be positive. And on top of that, this will be increasing because, like we said, this grows a lot faster than the numerator. Okay. So now we've verified that we can use the integral test. So we can rewrite this limit as t goes to infinity of the integral from 0 to infinity n e to the negative n squared, x e to the negative x squared dx. Alright, and so here I'm going to use another u substitution, right? We shouldn't automatically assume that this is going to be integration by parts, right? Even though we've got a polynomial, we've got an exponential, we're going to do u substitution here because we can do u equals negative x squared and cancel out our x that's multiplying with the exponential function. So this will become negative 1/2 limit as t goes to infinity of the integral, this should have been a t up here, the integral from 0 to t of e to the u du, which will give us negative 1/2 limit as t goes to infinity of, let's see, we'll have e to the u evaluated from 0 to t, which will give us negative 1/2 limit as t goes to infinity of e to the t minus e to the 0. And I've made a huge mistake here, which is that I did not change my limits when I u substituted. So this should have been a negative t squared, and this should have been a negative t squared, right? So super important step right there to change our limits. And so then we're evaluating from 0 to negative t squared. And this will give us, alright, sorry, this is still, whoops, so this should have been e to the negative t squared. That will give us, well, e to the negative t squared is the same thing as 1 over e to the t squared, so when we plug in infinity, that part will go to 0. So we'll get negative 1/2 minus e to the 0, so that's negative 1/2 times negative 1, which will give us 1/2, which means that the sum also converges. Okay, now let's move on to example 5. For example 5, we can think about using the test for divergence first, but we've got all these n's on the bottom, and so this denominator is going to go to infinity, so we'll get 0. So we know, once again, that the test for divergence fails. And so we'll go ahead and start using our integral test. Right, and so I want to make sure, alright, I'm going to get rid of these equal signs because this is not equal to the sum. Right, and I don't want to confuse anybody with this. Right, so once again, the reason I'm getting rid of these equal signs that I was putting like here is that this is not equal to this sum. Alright, so then this is going to be, let's see, we'll rewrite it as an integral for our integral test. So I'll have the integral from 2 to infinity of 1 over x square root ln x dx. Okay, so then what I get here, well, first I need to verify that we can use the integral test. We're not plugging in 0 on the bottom, so we're good. We're not plugging in negative numbers either, so this is going to be a continuous function. It's also going to be positive. Now to verify that it's decreasing, what we should look at is that x, if we take just x in the interval from 2 to infinity, these terms are getting bigger and bigger. Now if I take square root ln x in the interval from 2 to infinity, ln x will be getting bigger and bigger. So the square root is going to get bigger and bigger as we increase our x values. All right. So that means that we're multiplying bigger and bigger numbers on bottom, so our fraction's getting smaller and smaller. So this is a decreasing function. Okay, so this will become the limit as t goes to infinity, integral from 2 to t of 1 over x square root ln x dx. And so now the u substitution that I'm going to use is u equals ln x, because then I can cancel out this little x value right there. So then this will become limit as t goes to infinity, integral from, I'm not going to make this mistake again, I'm going to change my limit, so this will be ln of 2, ln of t, and so this is 1 over, let's see, the x's would have canceled out, so we'll just be left with square root u du. And I'm going to go ahead and rewrite this real quick, since 1 over square root u is the same thing as u to the negative 1/2 du. Okay, so then this will become the limit as t goes to infinity of, let's see, we should have 2u to the 1/2 evaluated from ln of 2 to ln of t. So this is the limit as t goes to infinity of, I'm going to go ahead and actually pull this 2 out. This is 2 times this limit. And we'll have the square root of ln of t minus the square root of ln of 2. And here we should see that this part is going to go to infinity. So we'll have infinity minus a constant, which is infinity. And then 2 times infinity gives us infinity. So this means that the sum also diverges. Now, remember that in section 7.8, we determined that if this a value right here is greater than 0, then the integral from a to infinity of 1 over x to the p dx will converge if this exponent p is greater than 1. And it'll diverge if that exponent is less than or equal to 1. Well, now we can turn this into what we call the p-series test. And here, I'm still going to be assuming that the a value is greater than 0. What the p-series test says is that if you have the sum from n equals a to infinity of 1 over n to the p, where we want to keep in mind the p's that we're looking at here, we're only looking at p's greater than 0, then this is going to be convergent if p is greater than 1. It'll be divergent if p is less than or equal to 1, but still greater than 0. The special case where p is equal to 1, we call that the harmonic series, and from this we can see that it diverges. So for example, here, what I'm going to do is I'll turn this sum into 10 times the sum as n equals 3 to infinity of 1 over n to the square root 2. So here's the things I need to verify. My a value is greater than 0, so we're good there. And then this square root 2 is greater than 1. So that automatically tells me that this is convergent. Right? So this is also another very nice test to use. Just like the test for divergence is very quick, this one's also really quick. If you get something that looks like a constant over n to some constant exponent, then you can pull that constant on top out, compare that exponent if it's in the range, right, if that exponent's greater than 0, then we'll automatically know if it converges or diverges. Here's another example. So I'll rewrite this as the sum from n equals 3 to infinity of 1 over, so n times square root n, that's n times n to the 1/2. So this is n to the 3/2. So what I notice here is that this 3 is greater than 0. This 3/2 is greater than 1. And so by our p-series test, we know that since p is greater than 1, this converges. Now notice what we're doing so far, we're not getting actual values that these converge to. So far, whenever you see a question that says, does this sum converge? You should automatically be thinking integral test, test for divergence, and this p-series test. Those are our main tests that we have so far for seeing if things converge or diverge. Okay, now let's look at this series. So here I'm going to rewrite this. This is 1 over 2 to the 1/4 plus 1 over 3 to the 1/4 plus 1 over 4 to the 1/4 plus 1 over 5 to the 1/4. And so what I notice is that this is the same thing as just saying the sum from n equals 2 to infinity of 1 over n to the 1/4. And so here we have this value is greater than 0, so we can use our p-series test. This one is less than or equal to 1, but still greater than 0. So that means that by our p-series test, this sum diverges. Okay. Now we're going to move on to what I consider to be the most complicated part of this section. This is going to be the remainder estimate for the integral test. If you don't get this right away, please don't be concerned. Just try to watch through the examples, come to office hours, get some more practice on it, and eventually we'll get it kind of just like settled into your mind. So the remainder estimate for the integral test says that if we have S sub n, right, where S sub n is going to be our nth partial sum, of some series that we know that series converges, right? So we can use something like, we know that it converges. So we can use something like the integral test or our p-series test to find out if a series converges. Once we know that it converges, we can start using the remainder estimate for the integral test to start looking at this new thing we're going to talk about. So it's very important that we notice that this is a convergent series whose sum is equal to S. So, for example, let's take something that we know what it converges to. So let's see. Let's say something like n equals 1 to infinity of 2 times, what do I want? 1/3 to the n minus 1. This is a geometric series, and so we know it's going to converge to 2 over 1 minus 1/3, which is 2/3. And so this is going to give us 3. Right? But suppose we just look at S sub 2. S sub 2 would be, let's see, the first term is going to be 2 times 1/3 to the 1 minus 1. So it's going to be 2 plus then our second term, so that was a sub 1. A sub 2 would be 2 times 1/3 to the 2 minus 1. And so that's going to be 2 plus 2/3. So that's like 2.666 repeating. All right. I'm just going to call it Let's just call it 2 2/3. So notice that this is actually pretty close to the actual sum, and that it's only off by 1/3. Now, this series was a pretty easy one to use, but what this remainder estimate is for is if we get a more complicated series, or we're using like a higher value of n for our S sub n, the remainder estimate lets us know how close we're going to be here, right? So what it says is that if we're using S sub n to approximate the sum S, and remember the remainder, so my remainder here is 1/3, we get that by doing 3 minus 2 2/3 equals 1/3, right? And so what this is the sum minus S sub 2 gives us what we call R sub 2, the remainder of S sub 2. And so that's why we say that the remainder is defined to be R sub n equals S minus S sub n. And we can write that out with this formula right here, which basically just says, okay, we took S sub n, which is the sum of the first n terms. And now this latter part right here is what the remainder is. The remainder is the sum of all the terms that come after A sub n. Okay. Now let's look at how we actually get the bounds on that approximation. So if we showed that this was convergent by the integral test, then we know that our remainder is going to lie inside these bounds. So, for example, if I calculate the integral from n to infinity right here of f of x dx, then I know my remainder has to be smaller than whatever that is. We call that the upper bound, right? So the integral from n to infinity is going to be the upper bound on the remainder R sub n, right? So it basically tells us whatever our remainder is, it has to be smaller than this. The lower bound would be this part right here, right? It's going to be this integral from n plus 1 to infinity of f of x dx. Now, to kind of talk about why that makes sense, you can go back and look at the picture on the first page and look at, okay, what does the integral from n to infinity look like as opposed to the integral from n plus 1 to infinity? Okay. Now, let's look at how we use this on example 9. So first, I'm going to get rid of all this stuff I've written in here. Feel free to write that down somewhere if you need it. All right, let's see how we use this. So we've been given some series, and we're first asked to find S sub 6. All right, well, to find S sub 6, that's going to be the sum of the first 6 terms. So that'd be 1 over 1 plus 1 over 2 squared, which is 4, plus 1 over 9. Whoa, I don't know what happened. Yikes. Plus 1 over 9 plus 1 over 16 plus 1 over 25 plus 1 over 36. So if you add those all together, that'll give you your S sub 6. Now we want to use the remainder estimate for the integral test to estimate our error, R sub 6, when we use S sub 6 to approximate S. So whenever it says we're using, so this is some key language, whenever it says we're using the sum of the first 6 terms as an approximation, that's the same thing as just saying S sub 6. Okay, so we're trying to figure out how close is S sub 6 to the actual sum S. To do that, I'm going to find our upper and lower bounds. So remember, the upper bound, right, so we'll mark this with a U. The upper bound is the integral from n to infinity. Well, Rn is going to be 6. So this is the integral from 6 to infinity of 1 over n squared. Right, and we already know that this thing converges by using the p-series test. So we'll get that this is going to be the limit as, and actually I should be using x here just to keep notation somewhat the same. So this is going to be the limit as t goes to infinity of the integral from 6 to t of 1 over x squared dx. And so this will give us negative 1 times the limit as t goes to infinity of, let's see, we should have, when we integrate x squared, that gave us our negative 1 out front, and then we should have x to the negative 1 evaluated from 6 to t. Okay, so then this is going to be negative 1 times limit as t goes to infinity of, let's see, we'll have x to the negative t minus x, sorry, we'll have t to the negative 1 minus 6 to the negative 1. So this first part, this will be 1 over infinity, so that goes to 0. Then we'll get negative 1 times negative 1 over 6. So this is going to give us a positive 1 over 6. And so that's going to be my upper bound. I know that whatever this remainder is, it has to be less than or equal to 1 over 6. Well, now I want to get the lower bound. To get the lower bound, I'll calculate the integral from 7 to infinity. Whoops. Keep using same colors. 7 to infinity of 1 over, x squared dx. And I already know from the pattern that I saw in U that this is going to be equal to 1/7. Right? And so that is our lower bound. And so what this tells me is that our remainder, r sub 6, is going to be greater than or equal to 1/7 and less than or equal to 1/6. So we actually have a pretty good approximation here. To say that this approximation is, between, that the remainder is going to be between these two values is pretty good. So now let me show you how we would write that in words. So I'm going to move this a little bit. So one way to interpret this, and let's kind of like block this off. All right. One way to interpret this is that, there we go, that's better. Okay. We can say that s sub 6 is no more than 1/6 bigger slash smaller. The reason I'm putting bigger slash smaller is because actually we're good. We're going to get a positive number. So we can do is no more than 1/6 bigger than s. Sorry, bigger slash smaller, because we don't know if it's above or below s. To give you an idea of what I'm talking about here, if we go back to this first picture, so here we could take a remainder. In this case, our approximation is going to be bigger than the actual sum, but in this case our approximation would be smaller than the actual sum. Right? And that's because of this extra space and this extra space. So that's why I'm writing bigger slash smaller. Okay. So going back down to here. So it's no more than 1/6 bigger slash smaller than the sum s. And it's, at least, it's going to be at least 1/7 bigger slash smaller than s, right? So I'm not sure if this will show up in the WebAssign, but I just want to give you an interpretation of what these upper bounds and lower bounds tell us. Okay, example 10. Let's consider the series given to us. We know that by the p-series test, this is going to converge. And we're asked to use the remainder estimate for the integral test to find the smallest value of n that will ensure the error in the approximation is less than 0.000001. Okay, the first thing I want to do when I get a question like this is whatever our error is, so this is going to be our error. The first step in this problem is to turn this into a fraction. So what I notice here is, being really careful, I have 1, 2, 3, 4, 5 zeros. So this is going to be the same thing as 1 over, now I need 6 zeros. 1, 2, 3, 4, 5, 6. Right. So this is going to be the same thing as 1 over a million. All right. Now, what we're saying is that we want this to be our upper bound. So what I need to do is, we know that the upper bound is given by the integral from n to infinity of f of x dx. And so that's exactly what we're going to do. We're going to do the integral from n to infinity of 1 over x to the 6th dx. Okay. Now, from here, we're going to calculate out this integral, and the one thing I want to remember is that this n is a constant value, right? If I choose, say, s sub 7, then this n would stay at 7. It's not going to be changing. So this is going to be the limit as t goes to infinity of the integral from n to t of x to the negative 6 dx, which will turn into, let's see, this should become negative 1/5 times the limit as t goes to infinity of the integral from, we're integrating. So I integrated x to the negative 6. That'll give us negative 5x to the negative 5. So we'll have x to the negative 5 evaluated from n to t. And so this becomes negative 1/5 limit as t goes to infinity of, so let's see, now we'll have t to the negative 5th minus n to the negative 5th. So this t to the negative 5th, that's going to turn into 1 over infinity to the 5th. So that'll go to 0. And we'll be left with negative 1/5 times negative n to the negative 5th. So this is negative 1/5 times negative n to the negative 5th. That's negative 1 over n to the 5th. And so this is 1 over 5n to the 5th. Or sorry, 5 times n to the 5th. Now, what we want is we want this to be less than our error, which is given by this orange number. So I'm going to write that down. We want what we calculated, which was 1 over 5n to the 5th, to be less than or equal to 1 over 1 million. So now we're trying to solve this inequality. So what I'm going to do is I'll multiply by 5 on both sides. So that means that 1 over n to the 5th has to be less than or equal to 5 over 1 million. This is a good time to simplify that. So this is going to turn into 200,000. Now what I would do, sorry, this is 1 over 200,000. Now what I'll do is flip my fractions and flip the inequality symbol. The other way we can see this is by multiplying by n to the 5th on both sides. and by multiplying by 200,000 on both sides. So that'll give us that 200,000 has to be less than or equal to n to the fifth, which means that n has to be greater than or equal to the fifth root of 200,000. That's a comma, not a 1. There we go. So we want n to be greater than or equal to that. Now this is a time where you pull out the calculator because none of us know the fifth root of 200,000 off the top of our heads. And so this means that we want n to be greater than or equal to, this is approximately 11.49 if you use a calculator and round to 2 decimal places. Now, what we should note is that n, when we're looking at values of n, these are always positive integer values, right? We start at n equals 1 and goes to infinity, and when we're plugging in values for n into our series, these are going to be like 1, 2, 3, 4, 5, and so on, right? We're not plugging in a decimal. So the smallest whole number that I can plug in that will satisfy this inequality is going to be n equals 12, right? And so that will be the smallest value of n that will get us within this error for our approximation to the sum, right? So that means if I calculate s sub n, if I calculate s sub 12, it will be no more than 1 over 1 million, bigger or less than our sum. Let's look at another example of this. So this one asks how many terms of the series from this given series would we need to add to find its sum within 0.0005. This is really similar to our last question. It's just phrased differently. This is another way of saying what's the smallest value of n such that s sub n will be within this range of error of our sum. And so I'm going to go ahead and rewrite that. That's going to be 5 over, I've got 3 zeros, so this should have 4 zeros. So 5 over 10,000, which is the same thing as 1 over 2,000. Okay. So that means that I want s minus s sub n to be less than or equal to 1 over 2,000, which is the same thing as saying I want r sub n to be less than or equal to 1 over 2,000. Okay, which is the same thing as saying that I want the upper bound to be less than or equal to 1 over 2,000. And we know that the upper bound will be calculated using the integral from n to infinity of, let's see, our function that represents that would be 30 over x to the fourth dx. We want this, since this is the upper bound, we want this to be less than or equal to 1 over 2,000. So what I'm going to start off by doing is calculating that improper integral. So we have that the integral from n to infinity of 30 over x to the fourth dx. So I'll rewrite this as a limit. So it's the limit as t goes to infinity, integral from n to t of 30 over x to the fourth. So I'm going to go ahead and pull out that 30. Okay, so we'll have the integral from n to t of x to the negative fourth. There should have been a dx in here. Alright, and then integrating x to the negative fourth, we should get negative 1/3 x to the negative third. So we'll have to pull out that negative 1/3. And then we'll have the limit as t goes to infinity of x to the negative 3rd from n to t. And so this will give us, let's see, that's going to be negative 10 times the limit as t goes to infinity of t to the negative 3rd minus n to the negative 3rd. We know that this part is going to go to 0, so we'll be left with 10 over n cubed. And so now going back to this part right here, we can say this is the sweet part of the problem because, it's circled in plum, and plums are sweet. But we're going to want 10 over n cubed to be less than or equal to 1 over 2,000. Okay. So now, if I divide by 10 on both sides, this will mean that 1 over n cubed is less than or equal to 1 over 20,000. So this means that we want n cubed to be greater than or equal to 20,000. Which means that we want n to be greater than or equal to the cube root of 20,000. And using a calculator, we would get that n needs to be greater than or equal to 27.14. So then the smallest whole number that will satisfy this inequality is 28. So what that tells me is that I need to add at least the first 28 terms to get within 0.005 of s, which is equal to the sum from I equals 1 to infinity of 30 over I to the 4th. All right, and so this will wrap up this section, but make sure you're practicing this a lot and paying close attention to the wording in the WebAssign problems. I think the most difficult part of this section, once you understand everything, like mathematically, is what are the questions actually asking? So if we pay attention to the wording in these problems, it can most of the time give us a hint in what direction we should go. Meaning that if something's asking me what something converges to, right? If I give you a series, I say, what does this converge to? You should never use the test for divergence, unless one of the answer choices is it doesn't converge to anything, right? But if you're given answer choices that are all whole numbers, suggesting that it has to converge to something, there's no reason to use the test for divergence because it's not going to give you any information on that. Similarly, you're not going to use the integral test because the integral test won't give you an exact answer. You won't use this remainder theorem because, again, this isn't giving you an exact answer. It's giving you an approximation, an estimation of how close we are, right? However, if something just says, does this converge or diverge, and it doesn't want what it converges or diverges to, then we start using things such as the P-series test, the test for divergence, stuff like that. So try to get comfortable with when do we use which test, because that's the biggest part of this week's material. And next week, it gets even more important because we'll get even more tests. Thank y'all very much, and I hope y'all have a great weekend.